This lecture is carboxylic acid reactions. If I can't finish in 1, then I'll go over to 3B. Otherwise, we'll try to finish it in one lecture, right? Because much of this should be a review, and if it's not a review for you, you should go back to some of these sections that I referred to and refresh your memory, all right? So I want to first go over how you learn how to make carboxylic acids, that functional group. And there were a variety of ways that you synthesize carboxylic acid. And one was oxidation reactions. As you see, there are 3 different ways that you learn how to do it. So if you started with some kind of primary alcohol, and you oxidized it with an oxidizing agent, and remember, because you're going from oxidation level 1 all the way to oxidation level 3, you need a strong oxidizing agent. And for example, sodium chromate was one of them that you learn. All right, and that's considered to be a strong oxidizing agent. Or you might have used chem 4, or some kind of strong oxidizing agent was used to go from oxidation level 1 to oxidation level 3. All right, so that's one easy way to make acids. Another way is so this method would keep the same number of carbons, and you're just doing a functional group interconversion. You could also do make carboxylic acids from alkenes or alkynes, and you basically took, for example, if you took a cyclohexene and you reacted with ozone, so this is an ozonolysis reaction under oxidative reagent, then you're basically cleaving the acetyl bond C, and in its place you're making carboxylic acid. So in this case, because we are the cyclohex we're doing with the cyclic compound, you would still have it same number of compounds. But if you did this with just a straight chain, then you would cleave here, and then you would end up with 2 compounds, 2 carboxylic acids, in which you basically are cutting it in half in this case, wherever the double bond was, where the carboxylic acid would be. And you could do the same thing with alkynes. And alkynes, you do the same chemistry, cleavage, and you get the 2 acids like in alkene. And in alkynes, you don't need another oxidative compound reagent to get to the carboxylic acid level. All right, and then last review of oxidation reaction is an alkyl benzene. So if you have a benzene group with some kind of benzylic carbon, then with the chromic acid, you basically cleave anything that is attached to that carbon, and that benzylic carbon becomes benzoic acid. So in this case, you're losing whatever carbon is attached to that carbon, and this is a quick and easy way to get benzoic acid out of benzylic compounds. All right. There are 2 other methods that you may not have seen that produces carboxylic acid very easily, and that is the Grignard method, in which you have some kind of halide, and you react with the Grignard metal, the magnesium metal, and you make the Grignard reagent. And then at this point, I think what you've seen so far is to react with aldehydes and ketones, and that gives you an alcohol. But if you were to react with carbon dioxide or dry ice in a solid form, you just throw it in. This is a pretty cool reaction. Then what you're doing is this is serving as an electrophile, and you are adding to the carbon of the carbon dioxide in the same exact chemistry that you've seen before, that you did with aldehydes and ketones. So this is serving the role of aldehyde and ketone, and then you just need an acid to get the proton, so that you get the carboxylic acid functional group attached to our group. All right, so this is a very useful synthetic method, because not only does it make carbon-carbon bond, it increases the carbon by one carbon skeleton by one carbon, and it gives you a very useful functional group, which is carboxylic acid. All right. Another way to make carboxylic acid is from a nitrile. So once again, you could do, for example, do an SN2 type of reaction, which you've seen before, to make the carbon-carbon bond connection, right? You've seen this in SN2 unit in 114. And now this carbon right here, remember, is triple bonded to N, so the oxygen level is 3, right, at this carbon. So all it needs is to go from nitrile to carboxylic acid is a hydrolysis condition in which you add acid and water, and you basically cook it, and you're hydrolyzing the nitrile group into a carboxylic acid. I'm not going to go over the mechanism of this, because we're going to go over that later when we cover the nitriles under the ester derivatives. All right, but for right now, you should know that this method is a very easy way to make carbon-carbon bonds, and at the same time, with another step, you could hydrolyze it to make carboxylic acid. All right. The rest of the time, I want to just briefly go over what kind of reactions that can you do with the carboxylic acid. So the first half is how to make carboxylic acid functional group. Once you make it, what kind of reactions can you react in? All right. So like I said before, the first reaction and the most important reaction probably is the acid-base reaction. So remember I said the carboxylic acid is like an organic acid. So with any base at all, the first reaction that it will do is an acid-base reaction, right? So this is going to serve as the acid. Base could be, you know, any of the base that you've heard of. Sodium carbonate, sodium bicarbonate, potassium carbonate. These are some examples of base that you could use. And when you have the base, it's going to come and deprotonate the proton and give the electron to one of the oxygens. So you're going to have a carboxylic acid salt with whatever metal you use. Is going to be the countercation. Okay, sorry about that. So you have your deprotonating. So it's a deprotonation reaction in an acid-base reaction, and the proton that comes off is the carboxylic acid proton. All right. And the second type of reaction that we already briefly went over is the reduction. But we looked at reduction in terms of aldehydes and ketones, and we use sodium borohydride as a reducing agent to go from oxidation level 2 to oxidation level 1. We have to use a strong reducing agent in order to go from oxidation level of 3 to oxidation level of 1. All right. So sodium borohydride is not strong enough to reduce oxidation level 3 compound. So it can't go from 3 to 2. but strong reducing agent is able to take an oxidation level 3 compound. It can't stop at 2 though, because it's too strong, and when it's at 2, remember this will also reduce. So the intermediate in going to the primary alcohol from the carboxylic acid is aldehyde. But aldehyde cannot be isolated, so it's an intermediate. And then as soon as it's formed, the reducing agent, because it's strong, takes the aldehyde to the alcohol, and that's what you isolate, is the primary alcohol with an oxidation level 1. All right, and the last reaction that I'm going to go over is a decarboxylation reaction, and this is briefly just mentioned in page 1060 of your book. And the reason why I want to go over this now is because it's pretty important reaction in our body, because this is the reaction that happens in metabolism of our food. All right, so let me go over what happens and what the requirements are, and then we'll look at what happens in our body. All right, so normally when you heat acids, nothing happens. But whenever you have an acid, a special acid that has a carbonyl group, not next door, but next door, so 2 doors down, when you heat that kind of compound, it automatically decarboxylates, meaning that it extrudes carbon dioxide. Okay, so the requirement is that you have a carboxylic acid, as you see here, and then the next carbon is called the alpha carbon, and then next is called the beta carbon. All right, and that's why this class of compound is called beta keto for this one, because you have a ketone and an acid. So this carbonyl doesn't have to be a ketone. It could be an aldehyde, it could be a ketone, it could be a carboxylic acid, it could be an ester, it could be any carbonyl compound. All right, so the name decarboxylation comes from the fact that it extrudes CO2, and the way it does that is as a cyclic intermediate. Okay, so this is all lined up here, and what it does is it sort of is hydrogen bonded intramolecularly like this in a cyclic fashion, and the 2 electrons that held the oxygen and hydrogen is used to make the CO2. And then this bond cleaves and goes next door. At the same time, the C-double-O grabs the hydrogen. All right. So this is the intermediate, and it's called enol, which is a C-double bonded C to an OH, which we'll be going over in the second part of this unit. But this is not stable, so it's not isolated. But there's a tautomerism occurring where the hydrogen hops over to this carbon, and then the C-double-O reforms. All right. So essentially, if you look at the overall reaction of this, so the overall is that this leaves as a CO2 gas. And then the hydrogen goes back to this carbon that used to be alpha to carboxylic acid. In other words, this is CH3, right? Oops, sorry. This is CH3 because this hydrogen essentially goes back to this carbon. So you are basically extruding out the carbon dioxide. And this is how we make carbon dioxide when we metabolize food. Okay, so in our body, this is oxalosuccinic acid, which is a common name for this succinic acid, and this is a one step in the TCA or the Krebs cycle. And notice that this is the carboxylic acid that is beta to this carbonyl, and that's going to be lost as a CO2. So the final product is going to be, the other carboxylic acid is going to be intact, but the second one is going to be extruded as carbon dioxide. And this is what are the key steps in forming carbon dioxide that we breathe out. And this is basically intermediate that Krebs cycle gets to as part of when the glucose breaks down. All right. So before I run out of time, this is the end. You should be able to do 20.10, and then you should also do the following page, which are drill problems that I put together for you. So you should be able to do all those problems. All right, before the